In this video, we're going to introduce some of the fundamentals of probability. So we're going to spend a lot more time on probability. In this section, we're just going to introduce some of the basic ideas and then we'll build on that. So probabilities are assigned to events. Think of events as possible outcomes, and they represent the likelihood of occurrence. In other words, how likely or how unlikely is it that we get a particular outcome in a particular situation. So probabilities can be expressed of one of two ways: percents, so that's going to range from 0% to 100%, or fractions and decimals, so that's going to range from 0 to 1. So any event that is certain to occur, in other words, it automatically has to happen, 100% positive, we know it's going to happen, that's always going to be assigned a probability of 1 if we're going to use a fraction or a decimal, or 100% if we're using a percentage. So events that are likely to occur, maybe they're not guaranteed, but they're likely to occur, are going to have probabilities that are close to this value. So say something has an 80% probability. Well, that means it's very likely. It doesn't mean it's guaranteed to occur, but it means it's very likely that it will occur. So the higher the probability, the more likely it is that something will occur. Now, an event that will never occur, something that's impossible, is assigned a probability of 0 or 0%, if you want to think about it that way. So in the same way, events that are unlikely to occur, maybe it's not guaranteed that they won't happen, but they're unlikely to occur, again, are going to have probabilities that are close to this value. So for instance, say an event has a 20% probability of occurrence. Well, that means it's fairly unlikely. It's not impossible that it could happen, but it's less likely to happen than an event that, for instance, has an 80% probability. So anywhere on the spectrum from 0 to 1 or from 0% to 100%, we can have events, we can have different probabilities. So we're going to look at two different types of probability situations. The one we're most used to seeing is called theoretical probability. So we're going to talk about what that means. So probabilities can be assigned to the possible outcomes of an experiment. Okay, now what does that mean? An experiment doesn't have to literally mean you're in a physics or chemistry lab doing an experiment, what we think of it as experiment. Think of an experiment as just an action or a sequence of actions. We're actually physically doing something, and this action or this sequence of actions we're taking has some possible outcomes. So in other words, maybe it could go one of 10 ways, something like that, in terms of what actually happens when we take this action. We have to be able to determine what all the possible outcomes are. So the set of all possible outcomes, all the different ways our action could go when we perform this action, the set of all possible outcomes is called the sample space. And so we're going to label that with a capital S. Notice it's a set. We do have that word set. We know what a set is. Sets are labeled with capital letters. So this particular set is going to be labeled with the capital letter S. Now, any subset of this event is, any subset of the sample space is what we're calling an event. So we're going to label that with a capital E. We could label that with other things as well. S is going to be specific to the sample space, but events could be labeled in different ways. So what do we mean by a subset of the sample space? Well, if we think of the sample space as combining all the possible outcomes, all the different ways our action could go, all the different things that could happen when we take this action, an event is going to be one or more particular outcomes that we're interested in. So maybe we're interested in how likely one particular outcome is, or maybe we're interested in how likely two different outcomes are together, maybe one then happening and then the other, something like that. So an event is just going to be some possible subset of all the possible outcomes that we could get from the experiment. So theoretical probability, what we're calling theoretical probability, applies when all possible outcomes are equally likely. In other words, we can determine in theory what could happen from this experiment without actually having to do the experiment. We can determine in the abstract what the situation could look like. We know all the different possible outcomes, and they all have an equal probability. So determining what could happen in any situation doesn't require that we actually perform the action. We can just talk about the action in abstract. So that's all really vague for right now. We're going to look at a bunch of examples and that'll start to make more sense. So how do we actually compute the probability in a situation like this? So we have our event E. E has N of E, so this is the cardinal number. Remember, this is the count. This is how many things are in this set E. So the event E has N of E, equally likely outcomes. So these are all the different outcomes associated with the particular event in question. In other words, these are the outcomes we're actually interested in. We want to know how likely are they. So an event E has this many possible outcomes, and the sample space for the experiment has N of S, equally likely outcomes. This is going to be the total number of possibilities. In this case, the theoretical probability of this event, of this combination of outcomes that we're interested in, is represented as P of E. So capital P stands for probability. P of E is a way of saying the probability of E. So the probability of E is going to be N of E divided by N of S. Now, what does that mean? It's the number of ways that the event could happen divided by the total number of possibilities in the sample space. So the total number of outcomes that we could get from this particular experiment. So the numerator represents the number of outcomes in the event. Keywords, in the event. In other words, the things that could actually happen. While the denominator represents the total number of possible outcomes for the experiment. So this event, all other possible events, all the possible outcomes, how many are there? That's going to be the denominator in this situation. So the numerator is always going to be lower than the denominator in general. It can't be higher, so they could possibly be equal, but otherwise the numerator is going to be lower than the denominator. So the numerator is the number of ways that our particular event could happen, and then the denominator is the total number of possible outcomes we could get from this experiment, this sequence of actions. So theoretical probability is commonly used to analyze games of chance because in situations like this, in general, every outcome is equally likely, and we can determine all the possible outcomes. We can determine how likely one is from the other because we have designed a game and we know a lot about the design. We know all the different possibilities. So for instance, coins, talking about coins, we have two sides, heads or tails. Those are the different outcomes, the two sides we have from flipping a coin. Dice, each die has 6 sides, labeled 1 to 6. So there's 6 outcomes if we roll a single die. Now cards, we do a lot with cards because there's a lot of different situations we can analyze with respect to cards. So in a deck of cards, we have 4 suits. Each one has 3 face cards and 10 non-face cards. So just so we're aware, the 4 suits, there's 2 red suits, there's 2 black suits. So the red suits are going to be hearts and diamonds. The black suits are going to be spades and clubs. So each one of those suits has 3 face cards. So that's going to be your jack, your queen, your king. And then 10 non-face cards. So an ace is considered a non-face card. So we have numbers from 2 to 10. And then we have the ace that's also considered a non-face card. So particularly with the cards, you might want to have a deck of cards handy. It's helpful to be able to look at a deck of cards from the standpoint of just analyzing the situations and making sure you have a visual component to the problems. Okay. So note that when you consider the theoretical probabilities of all possible outcomes in the sample space, in other words, say we consider the event to be every possible outcome, the sum of the probabilities is always going to be 1. So if we look at every possible outcome individually, take the probability of every individual possible outcome, and then add up all those probabilities, the sum, the outcome of that is always going to be exactly 1. Okay. So let's look at a situation involving a coin. So consider the situation in which you toss a single fair coin. So what does fair mean? Fair just means it's balanced. Imagine a perfectly manufactured coin. It's perfectly weighted. It's got heads on one side, tails on the other side. In other words, if we flip this coin, we know that it's equally likely that that coin lands on either side. So we want to define the sample space, then find the probability of the coin landing tails up. Okay, now again, sample space just means look at the experiment, look at the action being taken, and list all the different outcomes you could get from taking that action. So our experiment is tossing the coin. That's the actual action we're taking. So the sample space is going to be all the possible outcomes we could get from taking that action, from tossing that single coin. So that means our sample space in this case is going to be heads and tails. We'll just call them H and T. Those are the only possible outcomes from flipping a coin. So those are going to be the two outcomes in the sample space. What we want to know is the probability of the coin landing tails up. So if we're going to use the formal definition of probability, it's the number of ways that our particular event, our particular outcome or series of outcomes, it's the number of ways that can happen, divided by the size of the sample space. In other words, the total number of possible outcomes. So what does that look like in this kind of situation? Well, let's start with the denominator. So the denominator is the total number of possibilities. Well, in this case, there's only two possibilities from flipping a coin, so the denominator is going to be 2. Now, we're interested in the event of flipping a tail when you flip. Well, based on the sample space, there's only one way we can flip a tail. So the numerator for our probability is going to be 1. So there's one way to get a tail out of the 2 total possible outcomes we can have for this particular sample space. So the probability, not surprisingly, of flipping a tail is going to be 1/2. It would work the same way if we were talking about heads. So there's one way to get a head by tossing a single coin out of the 2 total possibilities, one representative of heads, one representative of tails. Okay, let's look at a situation involving dice. So a fair die, so die is just the singular of dice. A fair die is rolled once. Now again, fair just means it's completely balanced. In this case, it's a perfect cube. It is equally likely to land on any side versus any other. So it's balanced, and we know that it's structured the way it's supposed to be. So we want to define the sample space, then find the probability of each of the following rolls. Okay, so our experiment is rolling a single die one time. So the sample space is all of the outcomes we can get from performing that action, from rolling a die. Well, if we roll that die one time, we have 6 possible outcomes. It could land on 1, it could land on 2, on 3, 4, 5, or 6. So there are 6 possible outcomes. These are the outcomes. So there are 6 elements in the sample space. That's going to be the size of our sample space. So now we want to know the probability of each of these possible outcomes. First one, what's the probability that we roll a 3? Okay, so again, if we go back to the definition of probability, the denominator is always going to be the total number of possibilities. In other words, the total number of elements in the sample space. Well, in this case, there are 6 elements in the sample space, so the denominator is going to be 6. The numerator is going to be how many ways we can get this particular outcome that we're interested in. Well, there's only one way to roll a 3. We roll the die one time. There's only one way to roll a 3. We just have to roll a 3. So there's one way to get the event of rolling a 3. So the numerator is going to be 1. So the probability of rolling a 3 is going to be 1 out of 6, 1/6. Now, what about rolling an even number? Notice that's not the same thing as rolling a 3. There's only one way to roll a 3, but how many ways are there to roll an even number? Now, notice the denominator is still going to be the same. So again, the denominator of probability is always going to be the size of the sample space, which in this case is 6. Well, how many ways are there to roll an even number? Well, we could roll a 2, a 4, or a 6. Those are going to be all the even outcomes we could get. So there's actually 3 different events, 3 different individual events associated with this one larger event. There's 3 different outcomes that represent the event of rolling an even number. So the numerator is going to be 3, and then again, the denominator is 6. Now 3/6, that's the probability expressed in terms of strict outcomes for our sample space for our event. But because this is a fraction that can be reduced, we do need to reduce it. So 3/6 reduces to 1/2. So what does that mean? Well, it means half of the time, if you're rolling a die, if you're rolling a fair die, half of the time you're going to roll an even number. Well, that's not surprising. Half of the events in the sample space represent even numbers. and then the other half represent odd numbers. So theoretically speaking, half the time you'll roll an even number, half the time you'll roll an odd number. Okay, now what about the event that we roll a number less than 5? Now strictly less than, which means 5 is not an option. We can't roll a 5. If it said a number less than or equal to 5, then rolling 5 would be included in this event. In this case, only numbers that are strictly less than 5 are included in this event. So there's 6 possibilities for rolling the die. So our denominator is 6. How many ways are there to get this particular outcome? In other words, how many outcomes are there in the event of rolling a number less than 5? Well, less than 5 means we rolled a 1, a 2, a 3, or a 4. So there are 4 different ways to roll a number that's less than 5. So our numerator is going to be 4 over our denominator of 6, which again reduces. So that's going to reduce to 2 over 3. So 2/3 of the time, if we're rolling a fair die, 2/3 of the time we're going to roll a number that is strictly less than 5. The other third of the time, we would roll a number that's greater than or equal to 5. In other words, the 5 or the 6. Now, this is kind of weird, a number less than 10, okay? Go back to the definition for probability. When in doubt, if it's hard to identify what's going on in a particular event, go back to the definition for probability and interpret everything very, very literally. Okay, so again, same experiment. So we're rolling a fair die. The denominator is always going to be the total number of possible outcomes, and we know that's going to be 6 in this case. Now remember, the numerator is the total number of ways you can get an outcome that's in this particular event. So this event is rolling a number that's less than 10. So we have to think about the sample space. How many elements in the sample space represent rolling a number that's less than 10? Well, if we roll a number that's less than 10, 1 is less than 10, 2 is less than 10, all the way up to 6. All of the possible outcomes in the sample space represent numbers that are less than 10. So there are a total of 6 different ways to roll a number that's less than 10. So our numerator is also going to be 6. So 6 total possibilities, and all 6 represent outcomes that would be in this particular event. 6 out of 6 gives us 1. From a practical standpoint, what that means, anytime we see a possibility of exactly 1, notice the other possibilities we have so far, they're fractions that are less than 1. This probability is exactly 1. If we thought of that as a percentage, that's 100%. So what that means is that anytime we perform this experiment, we roll a die. It is guaranteed we are 100% likely to roll a number less than 10. There's no way not to roll a number that's less than 10 because all of the possible outcomes represent numbers less than 10. So the probability of that particular event is going to be 1 because it is guaranteed that that event will take place whenever we roll a die. Now, what about rolling a number greater than 6? Okay, so again, go back to the definition. Sample space has 6 elements, so the denominator is going to be 6. Now, how many outcomes represent in rolling a number that is greater than 6? Well, we can roll a 1, a 2, a 3, a 4, a 5, and a 6. None of those outcomes represent a number that is greater than 6. So there are 0 ways performing this experiment. There are 0 ways to roll a number that is greater than 6. So our numerator is going to be 0. 0 divided by 6 is going to be 0. So this particular event has a probability of 0. A probability of 0 means it's impossible. It means there's no way we can perform this experiment and get this particular outcome or this particular combination of outcomes. None of the outcomes in the sample space represent rolling a number that's greater than 6, so that event has a probability of 0. Now let's look at cards. So again, you may want to have a deck of cards there with you just so you can reference that. You can have a visual, particularly if you don't play cards and you're not super familiar with what a deck of cards looks like. It may be beneficial to have one to physically look at this point. So we're going to assume we're dealt one card, only one card from a standard 52 card deck. Now we're going to assume the deck is fully shuffled. So when you get a brand new deck of cards, when you break that out for the first time, all of the suits are in order. All the cards are pre-ordered. Typically you have your jokers at the front of the deck. So 52 card deck that's fully shuffled, jokers are taken out. In other words, because it's fully shuffled, because the shuffle is random, we're just as likely to get any one card versus any other card. We don't know where anything is specifically in the deck. The deck's been well shuffled, so all draws are equally likely to all other draws. So again, we want to define the sample space, and then we want to find the probability of each of the following deals of a single card. Okay, so our experiment is dealing one card from the deck. That's the action we're taking. So the sample space is going to be the total number of ways we can get an outcome from performing this experiment. Well, if the experiment is dealing one card, then the total number of outcomes are going to be 52, because the total outcomes, or the different outcomes, are going to be each of the individual 52 cards in the deck. Now, I don't expect you to make a list, but you do need to understand what that represents. That represents the individual 52 cards in the deck. That's going to be our sample space. The most important thing here is going to be the size of that space. So in this case, the size of that sample space is going to be 52, because again, there are 52 possible outcomes from dealing one card. Okay, so let's look at some events here. Number one, what is the probability that we deal a king? Well, from our experiment, there are 52 possible outcomes, so our denominator is 52. How many ways are there to deal a king? Now again, this is one of those points where if you don't know too much about a deck of cards, you want to look at a deck of cards, and odds are you want to look at a non-shuffled deck of cards, so it's going to be easier to find individual cards in the deck. Well, a king is a type of card. Each suit has a king in it, and it has only one king. So if there are 4 suits, there are going to be 4 kings. There's going to be the king of hearts, the king of diamonds, the king of spades, the king of clubs. So there are 4 possible outcomes in this event. There's 4 ways that this particular event could happen if we're dealing one card from the deck. So our numerator is going to be 4, and our denominator is going to be 52. This is going to reduce to 1 over 13. Now, how do you reduce something like this if it's not obvious what to do? I would start just by looking at the fact that those numbers are both even. They're both even numbers. So 4 out of 52, we can at least reduce that by a 2. Now, here's another option if you've got this particular scientific calculator. 4 out of 52 is a fraction. So let's take 4 divided by 52. Let me turn it on, clear. 4 divided by 52. Okay, that's going to give me a decimal. I want to convert this to a fraction. So right above here in table, it has F and D. That means convert between fractions and decimals. And it's in green, which means you're going to use this button, but you're going to use this button after selecting second. So if we take 4 divided by 52, which is what our probability is, this would be a decimal version of our probability. We want to convert that to a fraction. So I'm going to hit second and table. This says convert it to a fraction, from the decimal to a fraction. I'm going to hit enter. And notice it converts it to a fully reduced fraction for me. It doesn't give me the 4 out of 52, it gives me the reduced version of that fraction. So that's a great button to use. Now you can also do that on a graphing calculator. Say you want to do that, you need some help reducing. I'm going to do the same thing. So 4 divided by 52, and again that's going to give me the decimal, same decimal. I can also convert to a fraction on the graphing calculator. I'm going to go to the math menu, which is going to be the same menu I use when I want to do a permutation or a combination. So I'm going to hit the math button. The very first option says arrow frac, which means convert to a fraction. So I'm going to highlight that and I'm going to click enter. So this is now saying take the answer from the previous line and convert it to a fraction. I'm going to hit enter again, and then again notice it converts it to 1 over 13. This is going to save you a lot of time reducing your fractions. These are not too bad, just because when in doubt, we know these are both even numbers. They could at least be reduced by 2, and then we could go from there. But once the numbers get to be especially large, and it's not entirely obvious would they reduce, those are going to be options to help us see whether or not our fractions can be reduced, and it's going to do the reduction for us if the fractions can be reduced. So that's going to be a great tool to use in these kind of problems. Okay, let's look at another one. What's the probability that we deal a heart from one card out of the deck? Well, again, how many total possibilities? 52, because there's 52 possible outcomes from dealing one card. Now, this does make the assumption that after you deal the king, you put it back in the deck. We have to assume we're starting with a fresh deck each time, fully shuffled fresh deck. What's the probability that we deal a heart from that deck? Well, 52 total possibilities. How many ways are there to get a heart from the deck? Well, hearts is going to be one of the 4 equally sized suits. There are 13 cards per suit. How do you remember how many cards there are per suit? Well, if you remember that there's 52 in the deck and there's 4 suits, then 52 divided by 4 is going to give you 13. So 13 is going to be the size of each individual suit. So there's 13 ways to get a diamond from dealing that one card. 13 out of 52. That's going to be the fraction we want. And we just showed that 52 divided by 4 is going to be 13. So 13 and 52 have that common factor of 4. So if we divide, or that's not really a good way to say that. 52 divided by 13, is going to be 4. They don't both have a factor of 4. We can reduce this to 1 over 4. So that's going to be our probability. So in other words, 1/4 of the time, 1/4 of the time, you're going to get a heart if you just randomly deal cards. The other 3/4 of the time, you're going to get one of the other suits, so a diamond, a spade, or a club. Now, what about dealing specifically the King of Hearts? Well, the King of Hearts is one specific card in the deck. So out of the 52 possible deals, there's only one way to deal specifically the King of Hearts, because there's only one King of Hearts in the deck. So the probability of any individual specific card is always going to be 1 out of 52. There's only one way to get each individual card, so the probability is going to be 1 out of 52. Now, what about dealing a black card? Well, what does that mean? Remember, there's 4 suits, 2 suits are red, 2 suits are black. So that means half of the deck is going to be black cards. Specifically, if there's 13 per suit and there's 2 suits of black cards, then there's going to be 26 black cards in total, 13 from each suit and then 2 suits that are black. So 26 out of the 52 possible deals. Again, that reduces to 1/2. So in other words, half of the time, you're going to deal a black card if you're just dealing randomly from a well-shuffled deck. Now, what about a face card? Face card means either a jack, a queen, or a king. We have to think about how many face cards there are on the deck. Well, there's going to be a jack, a queen, and a king for each of the suits. There's going to be 4 suits in total. So that means there are going to be 12 face cards out of the 52 cards in the deck in total. 12 over 52 reduces to 3 over 13. And remember, you can do that in the calculator using that convert to fraction button. Now, what about a black face card? So it's 2 requirements at the same time. It needs to be a black card. It needs to be a face card. Well, think about all the different cards that would meet this requirement. We know, again, there's 52 in total. So our denominator is 52. We need to get a card that's both a black card and a face card at the same time. Well, we could have the jack, the queen, the king of spades, or we could have the jack, the queen, the king of clubs. That's a total of 6 cards. So any of those cards dealt would be considered an outcome in this particular event. So there's 6 ways to perform this particular event, 6 outcomes divided out of the 52, which reduces to 3 out of 26. Notice this is the first one we have so far, or actually this one was the first one. I was going to say, notice with these 2, we can't reduce to a denominator or to a numerator of 1. That's okay, sometimes that's going to happen. So this one reduced to 3 out of 13, this one reduced to 3 out of 26. Sometimes your reduction will not take your numerator to 1. It's possible. Okay, what about a card greater than 3 but less than 7? So if we were to write that using inequality notation, 3 is less than x and x is less than 7, using that compound inequality. Well, what kind of cards are represented in that event? Well, if it's greater than 3 but also less than 7, that could be a 4, a 5, or a 6. Those would be the cards that we're looking at. Now, it doesn't say they come from a specific suit or they're a specific color, so we have to consider all the possibilities. So we have a 4, a 5, or a 6 from each of the 4 suits. So 3 cards in total, 4 suits. Those 3 cards are located in each of the 4 suits. So there's going to be 12 ways to deal a card that's greater than 3 but less than 7. 12 out of 52 reduces to 3 out of 13. Notice we have 2 matching probabilities. So the probability of dealing a face card is the same as the probability of dealing a card that's greater than 3 but less than 7. In other words, each of these 2 events is equally likely. There's the same number of ways to get each of those particular events, to get those individual outcomes, so the probabilities are going to be the same. Now, what about the probability that we deal a card that is black or red? Okay. Well, again, go back to the definition. 52 total possibilities, so our denominator is 52. Well, how many ways are there to deal a card that is either black or red? Well, if you think about the cards you could deal, every single card you could deal is either a black card or a red card. There aren't any green cards, there aren't any blue cards. Any card we deal is going to fall under this combination of requirements. It's either going to be a black card or it's going to be a red card. So all 52 outcomes out of the total of 52 represent dealing a black card or a red card. So 52 out of the total 52 is going to be 1. So what that means is the event represented by dealing a card that is black or red is guaranteed. If the probability is 1, it means that event is guaranteed. So anytime we deal a card, it's either going to be a black card or a red card. Now, what about the probability of dealing a red spade? 52 possibilities in the sample space. Well, how many ways are there to get a red spade? Well, spades are a black suit. How many ways can we get a red card from a black suit? Well, we can't get any. If it's a black suit, there aren't any red cards in the suit. So there are 0 possible outcomes in this particular event. There's no way to get a card that fits into this particular event. So 0 possibilities out of the 52 in total. 0 out of 52 reduces to 0. And again, any event that has a probability of 0 is impossible. In other words, it's impossible to deal a red spade from a deck of cards. Okay, so that's just a little taste of theoretical probability. Games of chance, typically we use theoretical probability with just because we know the rules, we know how the games are structured, and we can base everything on just what happens in the abstract. Now we have a different kind of probability called empirical probability. So empirical probability applies when we can observe how frequently an event occurs. In other words, think of the experiment as being something we've actually done. It's not something we're just discussing in the abstract. We're basing our probability on actual data that we've gotten from actually physically taking a particular action. So when we compute empirical probability, it's still going to be basically the same ratio, numerator, denominator. The denominator still represents a total, but now we're talking about actual things that have occurred, not just theoretical events that could occur, but actual things that have occurred. So we still have a total number of possible things that could happen. The denominator based on empirical probability is going to be the total number of observed occurrences. Think of that as the number of times you performed your particular experiment. So say you performed an experiment 50 times and logged the outcomes for each of those 50 trials. That's going to be your denominator. It's going to be the 50 total times you performed the experiment. Well, we're interested in a specific event. In other words, a specific outcome or combination of outcomes that could have occurred based on this particular experiment. So the numerator in this case is going to be the observed number of times E occurs. In other words, if we look at the data from all the events that took place, all the times we ran this particular experiment and recorded the data from the trials. The numerator is going to be the number of times we got the particular outcome that we're interested in, the particular outcome associated with this particular event. So same idea as with theoretical probability, we're just looking at actual data. So it's going to be the number of ways we got the outcome we wanted, the one we're interested in, divided by the total number of outcomes we got, which in this case is just going to be how many times we ran the experiment. So for example, in 2015, there were approximately 254 million Americans ages 15 or older. The table below shows the distribution by marital status and gender of this population. Numbers in the table are expressed in millions. So let's look at how this is organized. So the rows correspond to binary gender, so male and female. And then the columns correspond to marital status, so people who are married, people who've never been married, so single and have always been single, people who are divorced, so no longer married but they were married, and then people who are widowed, so in other words they're no longer married just by death. The totals are in the column to the right and the row on the bottom. So that means 123 million men in total, and then 131 million women in total. Now the totals at the bottom, that's going to be the total number of married people, the total number of people who were never married, the total number of divorced people, and then the total number of widowed people. And down in the very bottom corner, notice if you add up each of the totals, either along that column or along that row, it adds up to a total of 254. So 254 million. In other words, everyone has been categorized. So what would the experiment be involved here? Think about just taking the census. So each individual collection of data for each individual represents one particular trial of the experiment. The outcomes are going to be determined from the table. So all the different ways you categorized a person, those are the possible outcomes for this experiment. Okay, so if one person is randomly selected from the population described, find each of the following probabilities. So event 1, the person is divorced. Well, how many possibilities are there in total? How many people do we have to choose from? In this case, we have 254 million. Now, because all the numbers are in millions, we don't have to write millions. We can just write the number of millions. So the denominator is going to be 254 because those are the total number we have to choose from. We have that many people to choose from. Now, we want the probability that a person is divorced. In other words, we pick a name randomly out of this table. What's the probability that we pick a name of someone who's divorced? Well, there's 254 possible outcomes. The number of ways we can pick a divorced person, there's going to be 26 ways, technically 26 million, but 26 ways we can do that. So 26 ways we get the outcome we want. So 26 divided by 254. Now, in these situations where we have particularly nasty fractions, in a lot of these situations, we're going to convert our probabilities to a decimal so that they're a little bit more meaningful. 26 out of 254 doesn't mean a lot to me. But if I were to take that and actually take 26 divided by 254, that converts it to a decimal. Remember, decimals can always be converted to percentages. So if we're interested in what that number really means, if we multiply that by 100, this is now a percent. So that's about 10.2%. So as a decimal to two places, we'll just say 0.10. So in other words, about 1/10 of the time, if we just pick a random name from the table, we'll pick a name of someone who is divorced. So 26 to choose from out of the 254 in total. Now, what's the probability that we pick a person that is female? Well, 254 to choose from. The total number of females we have to choose from are going to be 131 or 131 million. So 131 ways to get an outcome in this event divided by the 254 in total. So let's see that. So that's going to be 131 divided by 254. And there we go. So if we rounded two places, that's going to round up to 0.52. So about 52% of the time, if we randomly choose a name, we'll choose the name of someone who is female, which means in this case, it's more likely to choose a female name than it is to choose a male name. The other 48% of the time, we choose a name that's male. In this case, it's more likely to choose a female name than a male name, although it's roughly half and half. Okay, now this is what we call a compound event. There's actually two things involved here. So the person has never been married and is male, both at the same time. So never married, so that means we're looking at the category of people who are single and have always been single, and is male, so never married. Well, there's 81 million of those in total. That's broken down by either people who are male or people who are female. We're interested in people who were never married and are male. So never married and are male. How do we tell where to look in the table? Well, we're looking for the intersection of the column and the row that we're interested in. In this case, this particular cell is going to be the one that represents our intersection. So we have 43 million people that meet these two requirements. So 43 out of the total 254, which is approximately 0.17. So about 17% of the time, we'll choose the name of a person who meets these two qualifications. And then last, suppose the person is widowed and is female. So we're looking at the category of widowed individuals and then individuals that are female. This is the cell where those two column row intersect. So that's going to be 11 people out of the total of 254, which is approximately 0.04. So about 4% of the time, we would choose someone who meets these qualifications. Now, this is a little bit misleading in terms of how empirical probability typically works. So notice in this case, we've actually surveyed 254 million Americans. That's the idea. We actually have data on all these people. In a lot of cases, empirical probability will be used to take a sample to represent a whole population. So say, for instance, we survey 1,000 people in Houston. We calculate the data for them, and then we use the data for them as sort of a model for the city as a whole. So based on what would happen, how likely it is that we choose a particular person from that sample, we can assume that that sample is representative of the population at large. So this empirical probability situation is a little bit different in the sense that we're literally just taking a name out of the whole list of names. In a lot of situations, empirical probability will be used to help us sort of extrapolate data. If we have a large enough sample, can we extend that to what we could expect for the population as a whole? So these are just some of the general ideas we'll have in terms of probability. So we know what an experiment is, we know what an event is, we know what the sample space is. All of these different ideas we're going to continue to use. We're just going to build on the complexity of the situations. Next video, we're going to look at how you count in probability situations. So we've talked about all these different counting techniques. Sometimes counting the number of items in the sample space, calculating the number of outcomes in our particular event requires the use of some of these counting techniques. So that's going to be what we'll look at next.